Hi guys, hope all of us are doing great. My name is Ernest and this is the Ernest Sciences and Mathematics TV channel. So today we are going to look at one of the concepts in chemistry, and this concerns the concept of the periodic table of the elements. Now this is going to assist us appreciate several areas that we are going to look into, especially on chemical reactions, a description of the elements and various properties, physical and chemical properties that we are going to encounter in different areas of chemical reactions and other areas, perhaps of chemical synthesis and etc. So for that particular case, then therefore, it is good for us to understand the various arrangements that have been put, or rather organized patterns which have been put to come up with the present display of the periodic table. Now, I've given this particular example for the periodic table, which basically has been organized in a color code. And I'm also going to use the second presentation that is going to give perhaps some of the labels which are missing in this particular case. Now, in us trying to look at the concept of the periodic table, this is going to assist us, as I've said, in trying to find a way of organizing these individual elements in different ways or in an organized manner for quick reference. And number two, this is going to assist us to monitor the trends which appear across the periodic table, either from the left to the right or from the right to the left and down each various columns that we're going to use a specific name, of course, in referring to them, and where some of the denotations are appearing this specific point and what are some of their reference. And also we're going to see why some of the elements have been given this specific part of the periodic table, and what of some of the procedure that were used in order to come up with this specific arrangement. Now, from a historical context, we're going to appreciate the fact that there are various scientists who came up with a different, of course, inputs insofar as the present understanding of the periodic table is concerned. And from this, we're going to see that Dmitry Mendeleev, of course, in the 19th century, is a scientist who came up with the idea of organizing the first 70 elements in form of a tabular form. And therefore, the subsequent input from other scientists like Henry Moseley and John Newlands, of course, came up with an idea of trying to consider the aspect of atomic numbers. And that's therefore, of course, from trying to organize the elements in that specific order from left to right and down these columns, basically relied heavily on what we referred to as atomic numbers. So from our earlier study on the atomic theory, of course, we had seen that one of the scientists, that is Dalton, proposed the atomic theory. And one of his postulates was concerning, of course, what we referred to as, of course, the atomic numbers, whereby we are going to consider the similarities insofar as the atomic numbers and the mass numbers are concerned. So in this particular case, I've discussed in one of our videos on how we can be able to represent an element, and the arrangement of elements in the periodic table are going to assume that specific format. Now, in addition to that, of course, we're going to see that the International Union of Pure and Applied Chemistry has come up with a systematic way of trying to represent these individual elements, and therefore we're going to mention one of them in that particular case. Now, in regard to that also, we're going to see that there is a particular aspect of arrangement or rather denotation of these particular letters that are appearing on the top here. And also I'm going to mention their relevance. And that basically refers to the concept of trying to keep a registry of these individual elements for the sake of clarity. So in this particular sense, of course, from the Dalton's argument, we're going to see that Dalton, of course, argued that atoms of an element are similar in all respects. That basically refers to the aspect of a shape and mass. And of course, we're going to see that his argument also added that individual atoms of an element are different from that one of another. And his argument, of course, as we go through the historical timeline, are going to be disputed due to the presence of some of the elements that we refer to as isotopes. Now, these basically are elements that are containing the same atomic mass and the same mass, different mass numbers, but the same atomic numbers. And for example, if I try to give an example of chlorine has an isotope of chlorine 35 and chlorine 37 for the mass numbers respectively. So from John Dalton's argument, that one posed a challenge in trying to organize the periodic table. And of course, the argument that atoms of the same element are similar in all respects, that one pertaining to shape and mass. Therefore, that one created a contradiction and needed clarity. So the organization of the periodic table is going to shed light on how we can be able to clear this particular case, or rather try to solve that particular challenge. And we're going to see that the organization of element in form of their atomic number down up from hydrogen to organethone, of course, is going to display an increasing of course atomic number from hydrogen to this last element, of course. Also, we're going to see others being displayed in these specific different color codes, and therefore that is going to give us a clue on the basic organization of this periodic table. Now, from our earlier discussion, I had mentioned that elements can be represented using particular symbols. Now, we're going to see that there are different rules and variations that we're going to encounter insofar as these specific elements are concerned. And this basically relies on particularly what maybe those elements are made up of. And then we're going to also see that from a historical perspective, there are some mythological concepts which are associated with these particular elements, or the specific geographical locations and some of the properties which are contained in this element. Now, in some cases, we're going to encounter situations whereby the naming of the elements, of course, have been done depending, or rather trying to give tribute to scientists who particularly discovered them, or the particular space in which these individuals hold in the scientific community. So in essence, I'm going to use this particular illustration for hydrogen in trying to give a summary of the naming of these specific elements which are contained in the periodic table. And all of them are going to assume that a specific format insofar as their names and symbols are concerned. So from this particular case, we're going to see that this letter that is given as H stands for the element symbol. And other elements, of course, are going to assume that specific format whereby they are going to contain the initials for those specific names, and some of them which I've mentioned depending on the geographical location, the names of scientists, the places where they are found, and some of the similar substances that those elements are going to assume. And some of them, as I've mentioned, are going to be named from the mythological concept or characters of historical characters, of course, which they are related to in some points in history. So this, of course, stands for hydrogen. And next, we're going to see that there's some specific numerical values which are going to be attached at the upper left part of these specific sections for each element in the periodic table. Now, this stands for the atomic number, which we had mentioned on the study of subatomic particles as the number of protons which are contained in this specific element, the nucleus of this specific element. The next, we're going to see that there is an IUPAC, a group that is going to be allocated for these specific names. And this also is going to appear in form of a numerical value that is going to be allocated on top of those specific symbols. And then next, we're going to see that this up part of the right corner, upper corner of the right part of this specific symbol is going to be a relative atomic mass. Of course, we have looked at this, which of course is a ratio between the average or the mean value for the atomic masses and the ratio between that and 1/12 of the carbon-12 isotope. And therefore, that is going to provide for us the relative atomic mass of individual elements which has been given an initial A. And then next, we're going to look at this particular case of what we refer to as CAS. And this, of course, is going to denote the registry of the chemical abstract services, which is going to give a unique identifier for these individual elements. So therefore, in that particular respect, therefore, we're going to consider this particular format in this periodic table. And of course, as I've given examples, we're going to see that some of the elements that we're going to consider, like elements with their atomic number, of course, of 99, in this particular case, we can just consider, for instance, the element like, of course, this was in borium, named after Niels Bohr, of course, who we had mentioned on the Bohr-Rutherford model of an atom. So therefore, we're going to see that particular trend being assumed across the periodic table. And some of the elements are going to be named after the geographical locations, like the francium that is named after France. And then, of course, we're going also to see that other names are like, of course, the promethium, which is going to be given a name depending on the mythological concept, which of course is a Greek legend, of course, which has got some connotation and history. So therefore, this is going to be the format that is going to be used in naming elements. And we're going to see a characteristic ending for majority of the elements in the periodic table, which are going to assume the suffix "-iam". And basically, the suffix "-iam" refers to, of course, the association that we're going to see of these specific elements with what we call metallic substances, or perhaps derived from a metal as from that particular case. So therefore, if I try to look at the other illustration for the periodic table, we're going to see the work of Dmitry Mendeleev, of course, that is in the 19th century, playing a vital role in coming up with the present version of the periodic table. Now, Dmitry Mendeleev organized the first 70 elements based on their increasing mass and, of course, the similar properties. We're going to learn later about the chemical and physical properties of different elements and the various reactions with the, of course, common substances that we know. If we try to look at this, of course, we have hydrogen, helium, lithium, beryllium, boron, carbon. And if we try to look at what we refer to as the atomic number, it is increasing in that specific order. So this is the very concept that Dmitry Mendeleev had relied on in trying to organize the first 70 elements of the earlier periodic table. And in that particular respect, of course, there are other subsequent scientists who came up or created a new version from this particular foundation and came up with the present organization of this specific periodic table. Now, Henle mostly, of course, determined the atomic number of elements and organized this in order for increasing atomic mass of these specific elements. Now, of course, there was an earlier proposal that was done by John Newland. John Newland, of course, had given a system that was based on increasing atomic mass. Therefore, we're going to consider this specific two aspects of atomic mass and atomic number in a parallel way, so that they assist us to understand why this specific array of elements have been placed at different locations. Now, and this is also going to depend on their chemical and physical properties as by John Newlands. And of course, we're going to see that from their specific input in this particular display of the periodic table, this is going to cater for also the physical and chemical properties that we're going to see being displayed in this particular case. Now, of essence for us is to note that as they were trying to do their work, they realized that there's a particular sequence whereby after every 8 elements, there's a repetition of the physical and the chemical properties. And therefore, John Newlands came up with the concept of the law of octaves in reference to that particular repetition for the 8 elements, which of course try to repeat that particular cycle that we refer to as periodicity. Therefore, apart from Dmitry Mendeleev mostly and John Newlands, there were other scientists like Rother Meyer, of course, that showed a connection between the atomic masses of an element and their properties. And this, of course, cemented on the work that had been done by Mendeleev, of course, who had, of course, insisted on this specific periodicity of the patterns that we have mentioned. Now, in this particular case, by arranging elements in increasing atomic number, of course, Mendeleev created these specific columns, which we are going to refer to as. Now, I'm going to use that second illustration for the labels that I'm about to mention. Now, this particular illustration, unlike the first one, is indicating the periods, which basically runs from the top to the bottom. And this is in order for increasing atomic masses of these specific elements as they were done by Dmitry Mendeleev. So therefore, this is going to give us a trend that is going to be displayed that obeys what we have referred to as the laws of octaves. And therefore, as we are going to allocate these different elements for atomic masses and atomic numbers, therefore, we're going to find that there are some gaps that are going to be displayed. and which basically are some of the gaps which are going to denote some of the missing elements in this particular aspect. So therefore, whenever elements that have were being discovered throughout some timelines in history were found to possess some similar characteristics, perhaps on the amount or rather the number for the atomic masses and the atomic numbers, of course, therefore they could be allocated a particular point and given a name, as I had mentioned, using the IUPAC naming system, or some of the procedure that I had mentioned, like a mythological character, or perhaps a geographical location, or trying to appreciate the work of a particular individual in the scientific community. So therefore, we have seen that arrangement of these specific elements according to what we have referred to as rows gave what we call periods. And in this particular case, we're going to see a display of 7 periods for the period 1, 2, 3, 4, 5, 6, and 7. And therefore, the columns are going to form what we refer to as groups. Now, in this specific display for this periodic table, we're going to see that there's a wide range of groups which have been displayed, ranging from number 1 and then to number 18. But of course, in whenever we're going to create some segments or division of these specific elements, depending on their specific rows as periods, and of course the columns are going to be referred to as groups. Now, to mention these specific groups are going to give us what we refer to as the number of electrons in the outer energy levels, which we basically refer to as valence electrons in one of our discussions. And then the periods, which basically are going to be referred into in some literature as the series, are going to give us what we call the number of energy levels that an atom has. And we're going to see that this is going to increase across the periods when we're going to discuss on the concept of the periodic trends. But there's one of the challenges that was encountered insofar as the development of the periodic table is concerned, whereby we're going to see that after many of the elements were discovered, there was this particular case whereby trying to arrange the elements in order of their properties and together in collaboration with the atomic masses posed a challenge, whereby we are going to discover that there arose some aspects of what we refer to as their physical and chemical properties. So therefore, the challenge that arose is that there's a number of elements which were out of order whenever they were trying to be organized insofar as their physical and chemical properties were concerned. And therefore, this was, of course, corrected by Mosley's particular description or rather arrangement of this specific table by trying to organize elements that contain a unique number of protons that we had referred to as the atomic numbers. Now, basically then therefore, that one led to a corrected version of the periodic table that in an essence catered for the increase in atomic numbers and atomic masses, and of course trying to allocate elements with similar properties at a particular section of the periodic table. And this of course came up with a repetition of chemical and physical properties that came to be known as the periodic law, which we are going to look at later in some of our discussions. Now, from this, of course, we're going to appreciate the fact that these specific elements are going to display various properties. And from the color code that I've given as one of the ways in which I'm going to do this representation, therefore, I'm going to classify these elements in various periodic groups or series. And I had mentioned earlier that the concept of periodicity basically referred to, or what we refer to as a periodic law, refers to regular variations or particular patterns or properties which come up due to increase in atomic number. And this basically properties I'm referring to the chemical and physical properties that are going to vary in a repeating pattern. So therefore, these periodic groups are divided into roughly 10 groups, which I'm going to mention in this specific. Therefore, from my second version of the periodic table of elements, I'm going to mention these specific different color codes which have been given to show elements with similar properties, or which have been shown to display similarities insofar as these particular patterns and characteristics mentioned are concerned. So the first, this particular first group of elements are known as alkali metals, excluding hydrogen, which of course have been given a different color code, which is basically a gas that, as we're going to see in the physical properties later. So these elements ranging from lithium, sodium, sodium, potassium, rubidium, cesium, and then francium, going to fall under the categories of alkali metals. And then the next group, which is 2A or group 2, is going to contain from beryllium to radium, what we refer to as alkaline earth metals. And these are going to display different properties, as I've mentioned, which are going to discuss later in the periodic trend. Now, there's this segment that contains this particular range of elements, which of course falls under the category of what we refer to as transition metals. And this basically are also going to be shown to display some unique properties. Now, there's this segment of elements in this particular group number 3, which of course have been given these 2 color codes. Now, the expansion of this has been given under these 2 series, which have given this particular point I'm indicating, which shows what we call the lanthanide series and actinide series. This also falls under the category of transition elements, which of course are going to be referred to as inner transition elements. Now, in our subsequent discussions, we're going to see that these specific lanthanides are going to be referred to as rare earth metals. And of course, we're going to see that their physical and chemical properties are somehow going to be having a closer relationship as compared to other elements in the periodic table. And of course, we're going to see that we've discussed about the concept of electronic configuration from the various quantum numbers that are given in one of our videos. I'm going to put a link in the description box below for that particular emphasis. So we're going to see that there's a special characteristic for this category of elements that we refer to as lanthanide series, whereby the electronic configuration, of course, are going to contain, of course, what we refer to a valence shell of the F subshell, and thus making them have somehow similar properties. And from this particular second case, for the inner transition element, we're going to see another series that is referred to as actinide series, which is also a range of 15 elements ranging from actinium to lawrencium, that also are going to have some unique characteristic. But to mention one of the unique characteristics is that they are going to display an aspect of course, instability, whereby majority of them, all of them actually are going to display what we call the aspect of radioactivity. So therefore, much of the radioactive elements are going to fall under this category. And apart from that, we're going to see that they are going to display some characteristic of being paramagnetic or biophoric, and therefore going to be one of the unique set of elements in the periodic table under the inner transition elements. So from that, of course, apart from the alkali earth metals, alkaline metals, transition elements, and the inner transition elements, we're going to have this particular range of elements that we refer to as the basic metals. And these are some of the elements that are going to fall under the category of what we refer to as S and P block elements. Now we're going to see the comparative discussion on S and P block elements when we're going to talk about some of the discussions on metals. And these are referred to as S and P block elements or representative elements because their valence electrons are going to contain the S and P orbitals that we had discussed earlier. So apart from this, what we refer to as the basic metals, we're going to have another range of elements which are referred to as metalloids, or sometimes they can be given as a name as semi-metals. So therefore, these are going to be elements which are going to display the aspect of metallic characteristic and non-metallic characteristic. So therefore, the characteristics are going to fall in between metals and non-metals respectively. Now for the next category of elements which are going to be displayed, referred to as non-metals, this range of elements, we had seen them being displayed, or rather being actively involved in that category of or class of chemistry that we had discussed on organic compounds. And basically, they're going to fall under the category of what we refer to as non-metals. Whenever we're going to discuss on the concept of a covalent bonding, they are also going to display much of their properties in that particular respect. So therefore, next we're going to see a class of group 7A of these specific elements, which are referred to as halogens. And from this particular case, we're going to see that most of the salt which are compounds, salt, of course, compounds are going to fall under the category of these elements, whereby we are going to see some of these elements combined with perhaps alkaline metals, alkaline earth metals to form compounds which are salt. And the last one is going to form part of what we refer to as the group number 8A, and that is going to form what we refer to as noble gases. Now, in order of reactivity, these are going to be inert, and therefore we are going to expect no reaction from those specific elements. But from their application, we're going to appreciate some of the areas in which you are going to find application, which are basically relevant in our day-to-day activities in the society. Now, one of the unique characteristics we're going to see insofar as naming of these specific elements across the periodic table is that these elements have a characteristic ending, whereby they are ending with the, of course, the suffix iam. And this basically, from its historical context, refers to the concept of elements that were particularly related to metallic substances, or rather perhaps thought to be metals at their time of discovery. Now, with the subsequent systematic way of trying to name these elements, there are some of the elements that we're going to see assuming or maintaining their historical definitions, and therefore are going to have their traditional names being maintained, or rather suffixes being maintained. Now, of essence for us is to try and understand the specific context under which these specific elements were found. And of course, in trying to interpret the trend across the periodic table is going to assist us in trying to figure out or discover new elements that are going to be displayed. And of essence, as I've mentioned, of course, we're going to look at the comparative study of some of these elements that we're going to see being displayed in the periodic table. And of course, that is going to give us an understanding of some of the chemical and the physical properties. Now, of course, I stated that there's an aspect of valence electrons which has been catered for in this specific case. And insofar as their electronic configurations are concerned, then therefore we're going to see that the inclusion of these noble gases, as we can say, is going to be of essence for us in trying to give a summary of the electronic configuration. And therefore, whenever we're going to do a study about the periodic trends, we're going to we're going to consider the atomic sizes of each individual element, and then the comparison between the subsequent elements which are going to appear across the periodic table. And therefore, that is going to give us a trend in the atomic sizes, and perhaps the ionization energy and electronegativity, and as well the ionic sizes across the period. And this is going to, of course, assist us in order to figure out or predict their reactivity with some common elements like air and water, and also their ion formation for cations and anions. And this is, of course, is going to assist us in trying to find various applications in which these specific elements are going to be contained. So our subsequent videos are going to be a series of short videos whereby we are going to look at these various aspects insofar as electronegativities are concerned, their reactivity, and of course various ways in which they are going to behave insofar as their melting points and texture, density, etc. are concerned. So catch us in our next video. I hope that this video has been comprehensive insofar as the historical context of the periodic table is concerned, and why some of the elements have been placed where they have been placed insofar as these specific color codes are concerned. So that is it for now, guys. Catch us in our next video, and check our link in the description box for various videos that we're going to do, which are going to follow this particular video. So that is it for now, guys. Bye. God bless you.